Recorded is rolling. Today's Tuesday, April 12th. We're going to do 4 circuits. So look at these Kirchhoff tables and waterfall models. This is the printed on this with the waterfall models is printed on the back side of the page that has the circuits on it. So here's what we do. We're going to warm up with a couple of circuits from this side. You guys remember yesterday we mostly focused on, we did this top 8, we were finding equivalent resistances. So from the point of view of the voltage source, the battery, like the more resistors you put on in series, the more it increases the total resistance. But if you put them on in parallel, well, that's like guys paying attention. That's like a team that actually decrease the resistance. And then again, like these complicated circuits that have like some mix, right? So from the point of view of the battery, what's the equivalent resistance? Now the next step would be to say, if you know the voltage source, whether it's 9 volts or 5 volts, what current results from that? That's why actually, if you look real close with these circuits on the bottom page, it's actually pairs of questions. Because what's the equivalent resistance? And then what's the resulting current given the voltage? Okay? And then what we'll do is we're going to flip over to the other side, look at these waterfall models, and get into Kirchhoff's rules. Now, Kirchhoff's rules tell you exactly how the current flows and what the voltage drop is across each resistor. There's rules for series, there's rules for parallel. I actually gave you guys a modified version of Kirchhoff rules. Kirchhoff rules, I don't know if you guys want to get technical definitions, there's a loop rule and there's a junction rule, but I gave you guys effective applications of those. So that is what we're doing today. It's gonna be kind of a tight fit, but luckily we have a couple extra minutes in this class, so let's go for it. I'm counting on this one to be the recording. So number 9 and 10, you guys see this one right here? Let's start with this one. Okay. Actually, number 9 and 10, there's something special about this one. What's this one? Maybe almost a trick question in a certain way. What's this one have that none of the other ones have?
It's a empty break in the
You're looking at this line in the middle?
Yeah.
This line in the middle has a special name. Starts with an SH. Short, calling that short. Okay, you ever heard like a short circuit? Okay. Now, if you want to do like a full short circuit, I would just like connect both leads with, say, a wire, which I don't really want to do because that'll drain the battery real fast, right? Also get very hot. My fingers. But this might short out part of the circuit. Do you guys see that this one right here? This R3 and this R2. I think these two are not even part of the circuit, right? Like here, here's the story of the current. The current leaves this battery. It's going around, goes through R4, doing flow positive charge, okay? Then hits this junction, looks to the left and sees a bunch of stoplights, looks to the right and sees like a 10-lane superhighway with no cars on it. Ooh, which way are you gonna take? Probably this one, unless, I don't know, maybe that's too ominous, like leads straight to the zombie apocalypse, but yeah, I mean, there's no traffic. So that is a path of no resistance. And electricity is kind of all like path of least resistance. There's no resistance on that wire. So that's your entire circuit right there. Your entire circuit for number 9. It's just R1 and R4 in what, series or parallel? Series, yeah, because it's just sequential, one after another. Thank you, gang. Right? So number 9, all you do, it completely ignore R2 or R3. R2 and R3 are not even part of the circuit. Just go straight to R1 and R4, okay? And just add those together. Now for me, I have 3 ohms, 6 ohms. That gives me 9 ohms. Okay. So did everybody do that on your paper? So on number 9, find R1 and R4. Those are the only ones on the circuit. They're in series with each other. Just add them up. Hey, you guys ever dropped any kind of electrical appliance in water and it doesn't work anymore? That's because that water, the conductive, shorts out the circuits on the inside. Right? Kind of acts like one of these. Okay. So everybody has the answer to number 9, right? Just add together R1 and R4. Okay. Now the follow-up question. If I tell you the voltage supply, like 5 volts, can you figure out what is the equivalent what current is being provided by what current is flowing through that circuit? So we're going to kick over to Ohm's law. You guys remember Ohm's law? I know this goes back a few days. Current is potential difference or voltage acting on some resistance. So we got current measured in amps is potential difference or voltage, and volts acting on some resistance in ohms. Okay, so like if you double the voltage, you'll double the current. If you double the resistance, you'll get half the current. Okay, you guys get that? Okay. I'm going to pop in my numbers. I know I have 5 volts supplied. Actually, I think everybody has 5 volts. You guys got 5 volts? right?
Yes.
And my total resistance is 9 ohms. So divide that out. I have this many amps. And that is an answer choice, so I am good to go. You guys good? Number 9, number 10? All right, we're gonna do one more from this side today. Thinking ahead a little bit, I do want to get you guys a lab with where I put all these Christmas lights and chargers in your hands. So probably tomorrow I'm looking at, and then do some other stuff on Thursday and then try to get back to AP stuff after that. So yeah, you guys getting the real short version of this. Okay? But let's do one so a bit more complex. Number 1516. You guys see a pair of questions here, 1516? Okay. So first question, equivalent resistance, and then the follow-up Ohm's law, but we'll worry about that later. Okay. Equivalent resistance. You guys remember yesterday I told you there's a process. We're going to find the voltage source. We're going to fly over to the opposite side of the circuit and then work our way back towards the source. So I'm looking at R3 right here. Right? It's being furthest away. Work back towards. Right? Ooh, I'm going to run into R2. R2 and R3 are connected how? Yeah. Parallel. Because by the time any electricity that gets to that part of the circuit, you guys see how it has to split? There's a junction right there, and it gets pushed through both of them simultaneously. So the math is going to be like 2 guys painting a fence. So this is going to be a multi-part process. Number 15. First thing was what's the equivalent resistance down at the tail end, okay, very deep in the circuit. So I'm going to do product over sum of R2 and R3. R2 times R3 over R2 plus R3. Okay, pop in my own numbers. I have let's see, 4 ohms, 5 ohms, 4 plus 5. Some number of ohms. Let's see what is 29. Okay. Looking at this many ohms. Okay. Guys got that? Product over sum, R2 and R3. Okay. Now I'm going to redraw the circuit. So got voltage source over here. I've got R1 I haven't touched yet. It's probably going to be the last thing we do. I'll go ahead and label it. My R1 is this many ohms, so I'll go ahead and write that in here. R4 I also haven't touched yet. They're like this many ohms. Okay. But R2 and R3 collectively, well, we just solved that. Okay. Guys hear that? All right, so working back towards the voltage source, next one I run into is this one up here, which is R4. This is R4 up here, right? Okay. Those two are connected how? Series or parallel? Definitely series, right? It's because it's sequential. The current, whatever current goes through this, also has to go through this. Okay. So can I just add those two together? Yeah. Yeah, that's exactly what I'm going to do. So this looks like this many ohms because I just add them together, right? That plus that is that. Okay. Then redraw the circuit. So I got this guy right here. This guy right here. Okay. Work our way back towards the voltage source. Okay, run into the very last resistor. These two guys are connected how? Yeah. Parallel. So can I do product over sum? That's exactly what I'm going to do. So let's do this times this over this plus this. Number of ohms. So this is our total, the total equivalent resistance for the entire circuit. Okay, that's telling me, I have to write it out here. This many ohms, the whole thing. And if you did the whole process right, I know it's a multi-part process, then you should have a corresponding answer choice for number 15. You should see one of those. So everybody have, everybody get something? Okay. Number 16, the follow-up. So we're still in the same circuit, But the follow-up question is, well, how much current is leaving the battery? So 16, gonna do Ohm's law, current equals potential difference on resistance. Now the voltage is 5 volts. I think I gave everybody these cell phone chargers for their papers. That's acting on, well, your answer from the last one. This many ohms. Looking at this many amps. How many amps? You guys got that? Okay. Now remember, amps, like current, is analogous to flow rate or traffic. So I'm trying to segue into the next thing that we're doing here. Okay. Say if I forgot like 2.27 amps, right? 2.27 amps leave this battery, right? Start flowing around, and then it's going to split. Right? Some goes this way, some goes this way. Then it's going to split again. Some goes this way, some goes this way. Okay. Now, if you add up everything, it still has to equate to this. So when it all joins back together and flows back to the battery, it's still 2.27 amps for me. Okay. But you got smaller numbers going down each of those branches. Okay. And if you want to figure out how much current goes along each branch, well, that's where you have to break out Kirchhoff's rules. And that's what we're about to do right now with these waterfall models. Okay. So you guys turn the page over to the other side. We solve some waterfall models. And so we're going to do 2 of these. I've had time to do 2 of these today. We're going to do number 1, number 2. Okay. Now, number 1, I think is pretty straightforward on this page because it's just 3 in series. Okay, so I got 3 in series. And then something complicated number 2, but we'll look at that when we get there. Okay. So first one first. Okay. So 3 resistors in series. Let's take a look at this table and figure out what's the layout, where we're going with the story. So I told you what each of the resistors is in ohms. Okay. And I also told you the voltage supplied by the battery, and that's everything I gave you. And what we're going to figure out, first thing we're going to figure out is what's the equivalent resistance perceived by the battery. Because battery's pushing up some resistance, so I'll figure that. Okay. We're going to figure out what is the voltage drop across each resistor individually, right? We're going to figure out what is the current flowing through each resistor. Right? They're using Ohm's law. And then also, what is the power across each resistor, like how many watts at each point. Okay. If you remember back to Friday, I know this was a few days back before the weekend, the way that Paul Hewitt explained this whole thing with his 12-volt car battery and those bulbs, he actually approached it from a micro point of view. He's saying, well, what's going on across each resistor? And then he added everything up and said, oh, all the current has to come together and like so many current amps flow through the battery. Okay. I'm doing it backwards of how he's doing it. I'm saying, first of all, what's going on macroscopically. So from the battery's point of view, what's the equivalent resistance and the current? Okay. And then we're going to dig into into Kirchhoff's rules and say, okay, well, exactly how does the current split and what's the voltage drop across each location? Okay. So we're going like macro to micro. Okay. So start with the equivalent resistance. Now, because these 3 are all in series, can I just add them up? Right. That's exactly what we're going to do. So this 3 ohms plus 2 ohms plus 1 ohm, that gives me 6 ohms equivalent resistance. So the battery feels like it's pushing against 6 ohms. Well, on my paper anyway. So sort of analogy you can make here with, solving these Kirchhoff tables, it's kind of like solving a Sudoku puzzle, right? Once you have a certain number on the board, then everything else is determinable, right? Okay. So next step, what's the voltage drop at each point? Well, here's where I'm gonna break out these. Wait, did I flash this up here today? I think I did. Okay, it's getting later in the day. I can't remember. Okay. Oh, speaking of getting later in the day, okay, I'm so sorry about this. Let me backtrack a little bit, just to you guys remember the last circuit that we did? This fancy looking one here. I was gonna wire this up for you guys. I've got it all put together and everything. So let me show you guys real fast what this would look like. Okay. Do you guys have a prediction which bulb is going to be the brightest bulb? 5 volts here. Okay. Of course, all my crystal slides are the same resistance. Okay. So let me see if I can orient this thing. This is going to from together there. It's like this. Like this. Okay. Here it is. Right, so be like this. So here's like the R1. This is gonna be like R4, and these two guys are gonna be R2 and R3. Okay. Okay, here we go. Yeah, that's right. You guys see that where R1 is, that's really bright, and where R4 is, it's almost as bright. It's a little bit dimmer. So my R1's really bright, my R4 is a little dimmer, and my R2 and R3, they are shining, but it's barely noticeable. They're barely on, but there's a little bit of current flow. That's it. Okay. All right. That's it. All right, now we're ready for those waterfall models. All right, so when you have a series setup, and all we have for number one is just a straight series setup, the current's the same everywhere, right? The initial current coming in is the same current across here, same current across here, kind of analogous to traffic, right? Same traffic has to go through all stoplights, right? It's only one-way street. Okay? But the voltage drop, remember, voltage is kind of analogous to pressure. Well, that's going to drop proportional to each resistor. That's what this one says. So for example, if resistor A is 3 ohms and resistor B is 7 ohms, so 3 ohms and 7 ohms, and there's a potential difference between these two nodes, okay? Then I could say that 30% of the voltage drop happens across A, and the other 70% of the voltage drop happens across B. That's exactly what this says, right? And so we're just going to apply that. Right. The only difference with this one is I have 3 resistors instead of 2, but that's okay. You can just modify that real fast. Number 1, what's the voltage drop across resistor C? Right, I'm going to go CBA. I'm going clockwise, like flow positive charge. Okay. Well, that would be, see, some ratio of the total voltage drop, or maybe supplied by the battery. Okay. I'm going to go resistor C over RC plus RB plus RA. Then just pop in some numbers. So resistor C, my paper says 3 ohms, so I'll put 3 ohms up here, then 3, 2, and 1 ohms, right? 3 plus 2 plus 1 ohms. It's got ohms over ohms, the ohms cancel out. All times, I have a 12-volt battery myself on my paper, 12 volts. Okay. So that is, let's see, 3 over 6, which is half of 12 volts. That's 6 volts. So I'm going to go up to my table and say across resistor C, there's a 6-volt drop. Okay. How about across resistor B or resistor A? Well, all you have to do is swap out the subscript. Instead of resistor C up here, it'll be resistor B, the same denominator. Instead of resistor C, it'll be resistor A for right? You guys can do that. So the voltage drop across B is will be resistor B, which is for me is 2 ohms out of 6 ohms. So ohms over ohms, right? Cancel out, times 12 volts. 2 over 6 is the third. 12 is 4 volts. And for resistor A, the voltage drop is, see, resistor A, I have 1 ohm acting compared to 6 ohms. It's 12 volts, which is 2 volts, 2-volt drop. Go write those numbers in. So there's a 4-volt drop and a 2-volt drop. Okay. Okay, so it's fine. I want to take a pause from the table to actually draw this waterfall. I meant to draw the waterfall. So let's draw the waterfall in right here. Because it's a really good analogy where these numbers you can pair up, say, okay, I see how that looks like a waterfall. So now this one's real straightforward. Remember the battery here, it's kind of like a pump. That's why I drew the pump, kind of like a battery. Okay? And I've got 3 waterfalls just in succession. So bloop, bloop, bloop. Okay? So stream leaves the battery. Stream leaves the pump, current leaves the battery, right? Got splash waterfall, splash waterfall, splash waterfall. Okay. And then it all routes back to the pump. It gets pumped up again and then goes on another wild ride and round it goes. Okay. Until the battery drains its energy. Okay. You guys have some colors going around. I have some colored highlighters. Oh, I got a box of colored highlighters up here if you want. There's some crayons, colored pencils, markers going around. Guess you don't have to use if you don't want, but I like coloring the voltage planes. So I'm gonna do this. Where remember there's a potential difference between these two leads. So I'm gonna use the color to represent like high voltage, like 12 volts up here. Okay. Then maybe that'll jump down to like a yellow plane, which is like this elevation. Like each color corresponds to some elevation. Okay. Maybe I've got an orange plane down here. Orange plane. And then everything's gonna drop off to this green plane down here. Just like that here. So it drops like that. Where and we filled up part of this table, and I want you guys to see how those table numbers, the voltage drops correspond to the picture. Right? Remember, voltage is analogous to pressure. So like I know if you dive deep down into a pool, the deeper you go, the more the pressure builds up. But that corresponds to sort of like the deeper the hydroelectric dam, if you have a really deep dam, right? That would provide more and more pressure. So more elevation corresponds to like more voltage, right? So my battery is kind of like a pump that's 12 meters tall, except it's 12 volts tall. 12 volts. That's like a 12-meter tall cliff. Okay. And it's going to drop, well, a little bit at a time. Now resistor C, I've got a 6-volt drop. So that's like this right here, 6 volts. Then resistor B, 4 volts. So this drop right here, 4 volts. Then resistor A is 2 volts. So 2 volts, right? Now my picture is not going to be to scale because I made up different numbers for everybody's paper. Everybody's different numbers, right? But if it was to scale, then this would be like a 6-meter drop followed by a 4-meter drop followed by a 2-meter drop. Is that? Do you guys see that the amount that the pump pumps up the water is exactly equal to the sum of the heights of the waterfalls? Right? That is actually what Kirchhoff's loop rule says. Kirchhoff's loop rule says if you can identify any loop within a circuit, I mean, this circuit is just a loop, right? Very, very simply, but this will work even for like, other circuits, just identify some loop, right? If you pick a point and go around the loop, the voltages have to sum to 0. That's actually what the loop rule says. Okay? And in this example, it gets pumped up 12 volts, and then falls down 6, down 4, down 2. That also sums to 0, doesn't it? And then you're back in the valley where you started. Okay, that's that. Next question, what is the current in amps flowing through each resistor? Okay. Well, couldn't we just use Ohm's law for this one? Okay. Like, I know that current is equal to potential difference on resistance, I equals V over R, that's Ohm's law, right? So I have 6 volts on 3 ohms, 6 volts on 3 ohms. This is for the current going through resistor C. And wouldn't that be like 2 amps of current? 2 amps. Well, for my numbers, of course. Is that? So doing 2 amps. Right? Now you might very quickly pick up a pattern here, right? Because all I did was take this many volts divided by this many ohms, and I got the current going through that part of the circuit. Well, couldn't I just kind of copy paste that procedure all the way down? Like V over R, like Ohm's law for the next row. 4 volts on 2 ohms. Ooh, that's also 2 amps. And then for resistor A, 2 volts acting on 1 ohm, that's also 2 amps. How about across the battery? 12-volt battery, 6 ohms equivalent resistance, 12 over 6 is also 2. Right? Now, you might not have the number 2 all the way down, you might not have 2 amps, but if you did everything right, then I guarantee you that you have the same number all the way down. It might be 3 all the way down, it might be 1.5 all the way down, right? But it's the same number, right? You guys got the same number all the way down? If you don't have the same number all the way down, then you made a mistake somewhere, okay? Because the fact that it's a series circuit, you guys remember this rule right here for series circuit? The current is the same everywhere, right? Because it's a one-way street for the traffic, right? You got that? And last step, the power in watts. Now here's 3 perspectives on power. You could go power is current times voltage, P equals IV. Or you could substitute in Ohm's law and do P equals I squared times R, or you could substitute it in a different way and get voltage squared divided by resistance, V squared over R. Okay. They should all tell you the same number of watts, right? The same power in watts. Okay. Maybe I'll just pick this top one because it's pretty straightforward. Okay. Sometimes, depending on the question you're asked, it's actually more convenient to use one of the other two equations. But let's do this one. I times V, current times voltage. Okay. So 2 amps times 6 volts. Here, I'll write that out here. If anybody wants to see this on the video. I've got 2 amps times 6 volts is equal to 12 watts. Okay, so wouldn't this be like 12 watts right here? Okay. Okay. And I can just repeat that procedure all the way down. Okay. So I times V, 2 amps times 4 volts is 8 watts. 2 amps times 2 volts is 4 watts. Guys, yeah. Okay. And now the very last cell. Okay, now before I write in the last cell, and that you guys can get it very quickly anyway, I want to tell you guys 2 perspectives on this very last cell. And in both perspectives should lead to the same number. And then if you get the same number both ways, then that means you did the whole table right. Okay? Or probably. Okay. So one perspective is the 3 powers above, like this many watts, this many watts, this many watts. That's how much electricity is being demanded by each of these resistors, right? These resistors might be like little bulbs, couldn't they? Possibly. Right? Right. So that's like electricity demand. Let's add that up. 12 plus 8 is 20 plus 4. That's like 24. So there are 24 watts being demanded. Shouldn't there be 24 watts supplied by the battery? Right? There's no other way this would work. Right? 24 watts demanded, 24 watts supplied. The other perspective you could do is you could just do I times V for like at the point of the battery. So 2 amps going through the battery, 12 volts supplied, 2 times 12 is 24. Hey, it's 24 watts either way, isn't it? Right? Whether you do I times V at the point of the battery, or if you add up the electricity demand and say that must be electricity supplied. Either way, it's 24 watts. You guys got that? Right? That worked out on your papers too? Okay. All right, and then I do have a follow-up question here. It says, circle the brightest bulb. Now, what physics variable will tell you the brightest bulb? Yeah, power in watts. Yeah, so whoever has the most watts. So for me, that is looks like 12 watts, which would be the resistor C. Now for you guys, it may or may not be resistor C. It might be one of the other ones, right? Everybody has unique paper. Okay. I forget if I mentioned this or not, but on your paper, trying to know if you did this right or not. Another trick you can do is see how all my numbers are whole numbers, right? Most of the papers only have whole numbers. There are a couple of papers out there that have like 0.5s in them. So you might have like 1.5 or 3.5 somewhere, but you either have that or whole numbers. So you don't have anything crazy like 0.78 or something. Okay. Okay. That's good. All right, next one. Ooh, this looks much fancier. Okay. Actually, maybe I want to start with the waterfall model on this before we even dig into the numbers. Okay. So what's going on here? Some current leaves this battery. Okay, okay, it's going to flow around and it's immediately going to split. And then part of it's going to go down a very tall waterfall all the way down to 0 volts and then go straight back to the battery. You see there's already a loop right there. Okay. Let me start to draw that waterfall. So it's going to split. Part of it's going to go across resistor D, but part of it's going to go across resistor E, which is a straight dive all the way down to the valley. Here's resistor E right here. I'm drawing a very tall waterfall for that. Splash. And then that goes back to the pump. Okay. So I just drew in resistor E right there. Okay. And here's where it splits. Okay. It's going to go, okay, there's going to be a voltage drop across resistor D. So a little waterfall right here, splash. Okay. And then the current that leaves resistor D, do you guys see it splits again? Resistor B and resistor A? Huh. And resistor B and resistor A, those are in parallel with each other. So it's going to split and we're going to have side-by-side waterfalls right here. So there's one waterfall. Here's another waterfall. Okay. Then the current that goes through resistor B and resistor A immediately joins back together at this junction. So I'm going to draw these streams coming back together. Okay. And one more voltage drop across resistor C, a splash. Okay. And then any current that gone through resistor C. Now the voltage has dropped to 0 and it goes back to the battery. Let's say back to this pump. Okay, just like that. On some waterfalls. Exciting. We can learn these voltage planes because we got a bunch of colors here. Okay, so I'm gonna put 12 volt, or wait, yeah, so I got 12 volts myself. 12 volt lead here. Okay, that's like this whole top elevation. It's at 12 volts. Okay. Then say anything that goes through resistor D, let's say it drops down to like this yellow plane. So that's like right here. And that actually splits. It goes across there through both resistor B and resistor A. Okay, it's going to join back together. So that's where this is coming back together. The streams come back together. Okay. Goes across resistor C and down to the lower voltage plane. Down to the valley. It's down here, down to the valley. Okay. So it's a waterfall model. That's good. You guys see this one's definitely gonna be more complex than the last one. So let's start off on this fun process. Remember what we did last time was first found the equivalent resistance. So yeah, let's do that, I guess. Equivalent resistance. So story is we're gonna start with resistor A because it's furthest from the voltage source. Work our way back towards the source. I run into resistor B, right? Back towards resistor B. Okay. Those two are connected how again? Series or parallel? Yeah, that's parallel, right? So can I treat the math like two guys painting a fence? So that's gonna be the first step on number 2. First math step is resistance equivalent, just for that deep buried part of the circuit, is resistor A times resistor B over resistor A plus resistor B. Product over sum. Two guys painting a fence. And for me, those numbers are 4 and 4. Oh, the fact that I have the same resistance on each one of those 4 and 4, now you may or may not have that. Okay. Hey, let's do a painting a fence analogy. If it was 4 hours for this guy to paint a fence, and this guy works at the exact same rate, 4 hours to paint a fence. If they make a 2-man team, how long to paint the fence? Like 2 hours, right? You guys see 2 hours? Okay. I bet the answer to this is going to be 2 ohms. You guys think it's going to be 2 ohms? Okay. That's like a shortcut you can do whenever you have 2 resistors parallel, same resistance each. The total resistance is half of either one of them. So let me show you. So if I do 4 times 4 over 4 plus 4, total ohms, I got 16 acting on 8. 16 over 8 is indeed 2 ohms. Okay. Now that's not the answer to anything on the table. That's just the middle step. Okay. So one step down. Okay. It's part of the process. We're working our way back towards the voltage source. I'm going to redraw that circuit. Redraw the circuit time. Voltage source here. I'll go ahead and just label the numbers for these different resistors. Okay, so my resistor E is listed as 6 ohms, so I'll label this guy 6 ohms. My resistor D is 2 ohms. My resistor C was also given as 2 ohms. And remember, this guy out here is actually an equivalent resistance, which is this number right here, which happens to be 2 ohms. My name. Good start. Okay, so this 2, this 6, and this 2, I pulled straight from the table. I just copied these numbers right here. This one, pop, 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 right? And this 2 came out of an equivalent resistance of A and B being in parallel, like product over sum. Do you guys paint offense? Okay. All right, so we're working our way back towards the voltage source, right? And then, ooh, I ran into these two guys at the same time. Hey, these three amigos are all connected how? Series, right? Because they're all like sequential. So can I just add those three up? You see right here. By the way, hold on to these middle steps because we're going to need these middle steps later for digging into Kirchhoff's. So I see a total of 2 + 2 + 2 is 2 + 2 + 2. It's 6 ohms right there. Just for me. Right. Okay. Redraw the circuit again. Working back towards the voltage source. Okay. Those two are connected, what, series or parallel? Go parallel, yeah, because the current splits, goes through both simultaneously, parallel. Okay, so do you guys paint a fence? And if you remember that shortcut, that you might already know the answer to mine. What's the answer to mine going to be?
3.
Yeah, you guys do see 3, right? Because 6 hours, 2-man team takes them 3 hours to paint a fence. Right, but I'm going to do product over sum to confirm that. 6 × 6 over 6 + 6. Number of ohms. That's 36 on 12 ohms. Yeah, that is 3 ohms. Yeah, look at that. Okay. And that right there is the total equivalent resistance for the entire circuit. It's as if there's that whole circuit is a single 3 ohm resistor. Okay. That is the answer to this box right here. Again, I was trying to make everybody's come up with nice numbers. So you either have a whole number or you might have like something 0.5. Okay. You probably have a whole number there. Okay. Next column, what's the voltage drop at each resistor? Okay. Now this is probably the most difficult column to figure out, but now that we've gone through one of these tables, you kind of see where this is going, right? Once we figure out all the voltage drops, the current will just use Ohm's law, I = V/R, chug, chug, chug. And power is just going to be I × V, chug, 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 right? So we're at the hardest step right now. What's the voltage drop? Okay. Now to get the voltage drop, start from the top, right? Resistor E. I bet if you guys know Kirchhoff's loop rule, if you really internalize that, you might already know the answer to what the voltage drop is across this resistor right here. Does anybody know or how to get it? Look at this loop, right? Or how about this waterfall model? Is if you get pumped up 12 meters, does this waterfall also have to fall down 12 meters? So if you get pumped up 12 volts, does there have to be a 12-volt drop across resistor E? Okay. And I'm getting 12 from because my paper says 12 volts. I have a 12-volt battery. Okay. Whatever your battery is, you just copy and paste that number right here. Boink. Okay. I said same number. Go and label the height of my battery. I got a 12-volt battery myself. 12 volts. All right. Now resistor D. Well, I know it's going to fall some number of volts that's less than 12 because it also has to fall again and then again. Right. So I mean, this waterfall can't be more than 12. I don't know, maybe it's like 4, 5, 6 volts, something like that. How are we going to figure this out? Well, let's go back to, remember I said to hold on to your middle steps for when you're finding equivalent circuits. This is exactly where this is going to be useful. So this was one of the middle steps. You guys remember that? Right. And I know from here to here, there was like a 12-volt drop. Okay. So that means from this node to this node, there's definitely a 12-volt drop. Whether you go directly across this resistor E, or if you go make a round trip around here, either way, it's got to be a 12-volt drop, right? So it's going to drop a little bit, a little bit, a little bit, proportional to each resistor. Because this does look like series, doesn't it? Series, right? You guys see series? Right. So I'm going to do this right here. Is ready to do that? Okay. So just playing off this. Okay. Now I'm just gonna write with my own numbers. Okay. The voltage drop across, actually, maybe let's do this a little bit generic first. Across D, this is for number 2 still, okay, is equal to, okay, I'm gonna set up a big old proportion. Along fraction bar, delta V total, sort of just in terms of variables. Right, so this is going to be resistor D over, okay, this is resistor D here, resistor D plus, and then there's A and B in parallel. You guys remember A and B were in parallel? Resistor A and B collectively. And then plus, and this was resistor C down here. Okay. So that's kind of like a formulaic version of the model that I'm following. But here's the numbers for that. Okay. So how the numbers pop in, this is going to go, so delta V at point D is 2 ohms over 2 plus 2 plus 2 ohms, all multiplied by, I know there's a 12 volt potential difference altogether. Okay. So it's 2 over 6, okay, do that, 2 over 6 is 12 volts. Okay. That's a third of 12 volts is 4 volts. Okay. So I know that's a 12 volt drop across resistor D. Or my number. 4 volt. Okay. Who has a question where any of these numbers come from? Who has a question where any number comes from?
I'm still confused on how you did the first one. Not the second one.
Are you talking about how far back to here?
Yeah, like for finding the volts for E.
For
The first
oh, you're talking about this 12
Yes.
volts? Yeah, okay. All right. So the short answer is however many volts the battery is, just copy paste that number here. Right. And the reason is that is Kirchhoff's loop rule. Right. Kirchhoff's loop rule says if you identify any loop in a circuit, and I see a bunch of loops in the circuit. So let's say the leftmost loop. Right. If you go around the loop, the voltage has to sum to 0. So I get pumped up 12 volts, and it goes down 12 volts, right? Up 12, down 12. And then the waterfall model, you guys can think 3 dimensions, right? If you get pumped up 12 meters, you're gonna fall down 12 meters.
Okay.
Right? Yeah, there you go. Oh, and also, hey, we know this one. This is now a 4 volt drop right here, because we just figured that out, right? Or whatever your number is. Right? Your number is different than my numbers. Right, next one, resistor C. Now resistor C is down here, right? But isn't it almost exactly what we just did? All you have to do for resistor C is just replace this resistor D with resistor C. It's the same denominator, same as before, right? It's the same battery. So none of that changes. So delta V across resistor C, voltage drop across C, it's just going to be resistor C, which for me is 2 ohms, divided by same denominator of ohms, all multiplied by the same battery. Okay. So for me, it's the same number. So go to my table here, 4 volt drop there. Okay. Now resistor A and B, right? Now, a couple ways you can think about this. I mean, my numbers look kind of nice because where's my, here we go. Okay. Here's A and B collectively, right? They're parallel to each other, but they're effectively acting as like this many ohm resistor. Okay. Now, I mean, if there's a 4 volt drop here and a 4 volt drop here, you guys see my numbers are going to work out. So it's also going to be a 4 volt drop. Okay. So I'll just treat this together as a parallel circuit. Okay. And then, I mean, it's the same math. We just did it sort of like twice already. So if I wrote it, it would just look like the same. Okay. So it's going to be the same voltage drop across each of them. Okay. Here's why. I mean, this is one reason I'm having you guys draw a waterfall model is so you can see how the numbers correspond. Remember, voltage is analogous to pressure. Think of it like elevation. There's a 4 volt drop there. There's a 4 volt drop here. Okay. Do you guys see how this 4 plus 4 plus 4 adds up to the 12 volt battery? Right? It has to. There's no other way. Right? The heights of the waterfalls, right, have to add up to 12. But well, except of course you don't want to double count the 2 that are in parallel, because of course resistors in parallel, right? That's like A and B, have to have the same voltage drop. You guys remember that? It's a rule. Right? It doesn't matter if they're wildly different resistances or not. They might be the same resistance. They might be like 1 ohm versus 99 ohms. It's going to be the same potential difference. Okay. It's just a rule of electricity. Okay, you guys got that?
So you're saying A, B, and C have to add up?
Well, how about a CD and, or hold on. You could do C plus B plus D have to add up to 12, or like the battery, right? Or if you like, if you go around the outside, this one plus this one plus this one, right? Okay. But just don't double count resistor A and resistor B because they're side by side, right? But these three heights have to add up to the full battery height. Okay. 12.5. Right. Any questions so far? That's right. Okay. Okay. So we're past the hardest part of this. Everything else from now on is a bit formulated, right? But keep your eye on the principles. Make sure that everything checked out makes sense too. What's the current through each part? So the current through resistor E. We're going to go over to Ohm's law, right? Ohm's law. So Ohm's law, current is voltage acting on resistance. Okay. So I'm looking at 12 volts acting on 6 ohms. That's 2 amps. 2 amps. Okay. So current through E is 2 amps. Right. That's think of it like gallons per minute of this waterfall, or if you like maybe the waterfall width. Is it a skinny waterfall or a thick waterfall? Okay. Well, maybe that's a relative question. Let's see how many amps are flowing through the rest of the circuit. Okay. 4 divided by 2, that's also 2 amps going across resistor D, right? Okay, so this initial split on my peak plane, 2 amps went this way and 2 amps went this way. It's like 2 gallons per minute and 2 gallons per minute. It's split exactly half and half. It then splits again on this yellow plane. And what do we got here on resist? Oh, whoops. Well, resistor C is way down here, so let's see that one. 4 over 2 is still 2. There's still 2 amps that flow through resistor C, which makes sense. Right? Like 2 gallons per minute down here. Okay. But then here's the middle part of the story. Resistor A and B that are in parallel with each other. What happens there? Well, 4 over 4 is 1 amp. And same story here. 4 over 4 is 1 amp. You guys see it splits? So that, say 2 amps came down here and split 1 amp and 1 amp. Is that? And it came back together. 1 plus 1 made 2 again. Right? And then this 2 and this 2, hopefully they combine to make 4. Let's see if they do. 12 over 3. Yep, that's 4. Right? So the battery is supplying 4 amps. It splits 2 and 2. 2 amps just flow back to the battery. Okay? Then the other 2, it splits 1 and 1. And those come back together. 1 plus 1 makes 2. Those 2 combine with the original, or the other 2 make 4. They go back to battery. Yeah.
I still don't get how you got the battery.
So it's Ohm's law. 12 V over R. Right?
Yeah. Okay.
So 12 volts on 3 ohms. 12 over 3 is 4 amps. Yeah. And then finish this off here. Power. I gave you guys 3 formulas for power. So pick your favorite one. Maybe I'll just do I times B because it's pretty straightforward. If you want to check with the other ones, you can. So 2 amps, 12 volts, and that'd be 24 watts. 2 amps times 4 volts is 8 watts. 2 amps times 4 volts is 8 watts again. 1 amp times 4 volts is 4 watts. 1 amp times 4 volts is 4 watts. Right? Right, now pause right here because I'm right at the end of this table. Okay, I hope I got this everything right. Remember, I told you guys 2 perspectives for this very last cell. Okay. This very last cell tells you the power supplied by the battery. Now, the power supplied by the battery, you could go I times B at the point of the battery, but let's go and do that. 12 times 4, that'd be 48 watts. That 48 watts also better meet the electricity demand from each of the resistors. So if you add up all the watts from each resistor point, it has to add up to 48. Let's see if it does. Right. What is 24 watts plus 8 watts plus 8 watts plus 4 watts plus 4 watts? I hope this is 48. Oh yeah, it's 48. So all good to go. So electricity supply meets electricity demand, and that is a complete table. right? All right, that is as far as I've been getting today. So, yeah, we'll call that a pause point on this adventure. If you have any questions, let me know. And oh yeah, since you guys are AP in my 5th period class, if you have registration packets, oh, I see some more registration packets coming in. Bring those to me. Those are due very soon. And I'll take this to guidance. Also, you guys remember, I don't have any formal homework for you guys this week because we're just taking a week to do electricity. But there's all those AP classrooms that are open. Oh, speaking of AP classroom, some of you guys were actually doing those, and you reminded me of something I forgot. Those old assignments I created that just opened up in the past few weeks. I did put an FRQ question on the end of a lot of those. I forgot I had to do this, but I actually have to go in myself and like score that. Now you don't have to type anything. I'll just like check some boxes. But then once I do that, you can actually see how you did on the whole thing. So AP classes, you guys, in your own agenda, your own planner, make your own assignments to go to AP Classroom and do a bunch of those for practice.